staying safe. Today, I have the great pleasure of introducing Professor Ronald Blab. Dr. Blab obtained his doctoral degree in civil engineering from the Technical University of Vienna. Now he's a full professor and the dean of the Faculty of Civil Engineering at TU Vienna. His main research areas include testing and modeling of fundamental mechanical properties of road engineering materials. Professor Blab is also interested in their application for improved and sustainable design and maintenance. Today, he will be presenting about HMA modeling. As always, please remain muted. Professor Blab will have 40 minutes for his presentation, and then we will have 20 minutes for discussion and questions. To ask a question, please go to the Participants tab and click on Raise Hand, and I will be calling you guys out for the question, or you can submit it in the chat and I will be happy to address it for you. Welcome, Professor Blab. The audience is all yours.
Thanks a lot, and thank you very much for the invitation to give a lecture in this series. I think it's also from my point of view, it's easier that I mute my video here. And I hope you can see my slides. Everything works well, otherwise please just give me a sign. Yeah, I'm talking today, I was invited to talk about the multiscale modeling of asphaltic materials, a topic which we are working now for 10-15 years here in my research team. But before I start with my presentation itself, I want a little bit introduce myself, and probably you wonder where the hell is Vienna and where is Austria. So here is a map of Europe, and Vienna is right in the middle, in the heart of Europe. Austria is a small country in the southeast of Germany, and we are speaking actually German here in Austria. So this is Vienna. Vienna is the capital. It is an excellent place to live, a city with a very high quality of life. And you see here the St. Stephen's Cathedral on the right side. And on the left side, with this cupola, this is the Charles Church, and right opposite to the Charles Church, there's our university. It's the Technical University of Vienna. Actually, it is the oldest. Our university has a very long tradition. It's the oldest German-speaking technical university. We called it then Polytechnicum. So a very long tradition, and this is the historical building like it looks nowadays. And today the Technical University is the largest technical university in German-speaking countries. We have about 30,000 students enrolled. We host 8 faculties, and one of these faculties is the Faculty of Civil Engineering. And as Dean of the faculty, I'm especially proud that we could recently open a very new fancy facility in fall last year. It's a material lab where all our labs are comprised and moved to this new facility, and also our road lab is now situated in this new building, which is about 5 to 10 kilometers away from the main campus here at TU Wien. So this was then I have just what is the Institute of Transportation. So one of 8 institutes at the Faculty of Civil Engineering is the Institute of Transportation. And you see here we have 3 research centers, and one research center is the research center I'm heading, the Research Center for Road and Airfield Engineering. And we actually have 3 groups, working groups, and the presentation I give together is mainly related to the working group headed by Professor Hofko, Bernhard Hofko, Some of you may know him. And Dr. Eberhard Steiner, he's our modeling expert. Okay, and that you can also put some faces to our team. This is during an outdoor activity. We have this kind of activity once a year, and it was last year, so before COVID, before the pandemic problems we had. And half of the team was in a climbing garden. It was a very fantastic, fantastic half day with my team. And the other half were near a very nice fancy restaurant, and they told me that they just enjoyed some soft drinks, but you know, let's be it like that. Okay, so this was a short introduction, and I will come to a motivation why actually we started this activity with the multiscale modeling. And I want to give you a short overview what are multiscale modeling of engineering materials, what are these multiscale models for. So multiscale models usually relies on establishing modeling toolkits and packages for solving material-related problems. And they can incorporate a broad array of methods over a vast range of both spatial and temporal scales. So one way proposed by the authors Lehtinen and Paulin in 2013 of organizing this type of multiscale models and demonstrating some of the spatial and temporal linkages is presented here in this figure, just to give an overview. And the modeling methods can be roughly divided in two categories, discrete and continuous methods on the basis of how they describe materials. For many engineering materials, such also as asphaltic materials or hot mix asphalt materials, the so-called process structure properties performance concept, so it's not so easy, PSPP method is applied. Actually, that's what we also considered. The PSPP concept is a template for seeking a solution to material design and optimization tasks. In such a context, the focus is either to understand what are the features and material nano and or microstructure which are most dominant in finding the optimal solution for the material problem at hand, or just to simply understand what are the features in the current material selection and mix design responsible for the observed behavior and performance of the material in a specific component setting. So within this PSPP concept, the mix design and material processing or manufacturing is tied to a comprehension to comprehend the resulting material structure and the structure following yields and coupled to material properties. All these links are established by combining both experimental and modeling approaches. So the material properties are then translated to material performance, and the material undergoes specific environmental conditions or loading mechanisms. So this was the starting point of our material or multiscale model. So based on this concept, I mentioned that started to develop such a multiscale model for asphaltic materials 10-15 years ago. And the first multiscale model, we extended it now in these different stages. The first multiscale model for asphalt was characterized like depicted here in this slide. So the asphalt was characterized by four what we call observation scales. The bitumen scales on the bottom here, with asphaltene and maltene morphology. Then the mastic scale with bitumen and filler, the mortar scale, which is mastic and aggregates with a diameter of a small of 2 millimeters. That's what we call the mortar scale. And then the asphaltic scale, where we have the mortar and aggregates with a diameter larger than 2 millimeters and air voids. Within each observation scale, the characteristics such as structure and material properties of the constituents present at this scale are taken into account. So moreover, changes in the scale characteristics resulting from mechanical loading and or environmental conditions, for example, changes due to the binder aging, can be considered at the respective scale of observation within these models. The objective of the multiscale model is to the determination of macroscopic material parameters such as stiffness was the first we upscaled, then susceptibility to permanent deformation, or fatigue, which then serve as input parameter in the analysis of flexible pavement. So the parameters are obtained by means of an upscaling procedure, and I will go into this upscaling procedure and in the mathematics a little bit deeper in the next slides. And with these upscaling procedures, we can bridge the scales from the bitumen scale to the macro scale. So if you, for example, want to predict the influence of the rheology of the change of the volume fraction of a new binder, we can introduce these changes at the respective scale, so at the bitumen scale, and upscale it to the macro scale, and can easily predict the influence on the expected performance. So multiscale models are, from my point of view, from our point of view, a logical extension of existing pavement design concepts. And if you once did or made the mathematics, it's easy to do all the material design and the structural design on the computer. So you don't have to do that many testings on the macro scale. And you know, testing is also always time consuming and also expensive. So actually we can here design materials, and especially asphaltic materials, from the scratch. That's a little bit our vision, or was our vision. So here some basics in respect to the mechanics behind it. So we are looking at what we call a representative volume element, RVE. And looking at this RVE, the macroscopic stresses, oh, I'm sorry, I think I go back here. Here is the continuous model. So the challenge of the formulation of the material models based on structural considerations and the application of respective homogenization schemes. So that's actually the problem, the continuum mechanics problems. I forgot this slide to explain it. So in micromechanics, materials are analyzed at the level of their microscopic constituents, and to consider the macro homogeneous and the micro heterogeneous material, we use this kind of what I already explained, representative volume element, RVE. And it's a law that this RVE must fulfill what we call the law of separation of scales. So it's written here at the bottom of the slide, which says that D represents the characteristic length of the material phases, and this D must, small d must be much smaller than L, which L is the length of the RVE, and capital L denotes the characteristic length of the geometry or loading of the structure built up by the RV. And to determine the homogenized mechanical behavior of the overall material, the correlation between the homogeneous deformations acting on the boundary of the RV and resulting averaging stresses are estimated by using the elastic or also the viscoelastic behavior of the material phases of the RVE, as well as the volume fractions of the different inclusions, and also the characteristic shapes and the interaction. So here, this a little bit the continuum mechanics behind the homogenization scheme. So looking at this RVE, the macroscopic stresses, capital S and the strain E. So you see it here, macroscopic strain and stresses. They are identical to the spatial average, which is written here, of the resulting kinematically compatible microscopic stresses, sigma, small sigma, or epsilon, across the volume of the RVE, which itself consists of several material phases I, it is written here, with the stiffness tensor Ci. So this is actually the basic continuum micromechanics behind this RV. Now we can apply, if we stay in the elastic domain, we can apply the superposition principle, which is written here, and we come to a so-called concentration tensor to explain the macroscopic strains by the microscopic strain field across the RVE. From that, the homogeneous stiffness matrix C homogeneous, written down here, is related to the stiffness metric Cx and the localization tensor Ax, written here. It can be derived just from the sum over all material phases of the product volume fraction Fe, written here, and the material phase, the volume fraction of the different material phases, Fe, written here, excuse me, and the concentration tensor, Ae, and of course, the related stiffness matrix, CIE, of the different inclusions in the RVE. So, and an estimate for this localization tensor is the so-called SLB tensor. And I will not go too deep in this homogeneous material tensor, but you see here, this is actually what we need to express from the macroscopic, the macroscopic stresses and strains. And within this homogenization tensor, we have the volume fractions of the different material phases, the material tensor, which is related to the stiffness of the material phases, this so-called SLB tensor, excuse me, which is related to the morphology of the material. For example, we can have spherical inclusions or needle-like structures. So here different mathematical solutions provided for this SLB tensor. And also, which is also very important, we can also include here particle interactions, for example, full band of the different material inclusions, or also adhesion models. Now we can apply different what we call homogenization strategies, and we used here two types of strategies for asphaltic materials. The one is the called Mori-Tanaka scheme, which is applicable and suitable for matrix inclusion type morphologies. So we have low volume fractions of the inclusions. So typically applicable for example, at the binder scale or on the mastic scale. And then we have this so-called generalized self-consistent scheme, GSC. This is applicable if we have highly filled composites materials with metric inclusion type morphologies. And this is typical for the mortar or the asphalt phase, where we have also included some air voids. Now, these schemes, these homogenization schemes are only applicable in the elastic domain. So we had the problem, as you all know, that we, with asphaltic materials, we are talking about viscoelastic materials. We had to think about how we can upscale these viscoelastic properties with the existing homogenization strategies. And here, in a first step, we introduced a rather simple viscoelastic model for the behavior of the bitumen. We call it the power law model. So we have, on the one hand, very elegant tools in our hands to consider the micromechanical behavior of the elastic materials. But on the other hand, we have to consider, in the first step, in a rather simple viscoelastic model, the viscoelasticity of especially the binder. Why did we use this type of power law model to describe the viscoelasticity? The advantage is that it's a good description. Actually, you see here the model. It's very easy. It's a spring model with a nonlinear dashpot. So we have a 3-parameter model, G0, K, and GA. You can easily fit this model from, for example, DSR measurements, dynamic shear rheometer measurements, which are easily performed in the lab on bitumen, on the bitumen scale. And we found out that this type of simple rheological model characterize especially the short and long-term creep very well with only these 2 parameters. So we choose a rather simple rheological model for to describe the viscoelasticity. And now, to provide a formally elastic and such very convenient description of the viscoelastic problem, the time-dependent creep compliance, which is part of this power law model, is represented in the Laplace-Carlson space. Here it is defined by the frequency variable P on the basis of this Laplace-Carlson space. Probably some of you already know the mathematics behind the transformation. And now the presented homogenization strategies, for example, what I presented, the Mori-Tanaka scheme or the self-consistent scheme, can be applied because we are now in a quasi-elastic domain. But when we solve the problem, of course, of the homogenization, we have to do the inverse transformation. To give the predicted B-related relaxation tensor of the asphaltic materials in a physically relevant format, the homogenized creep compliance has to be back transformed, as I mentioned, into the time domain. And here we are using the so-called Stehfest algorithm for a pointwise back calculation of the viscoelastic behavior of the composite. So this is a little bit the background of the homogenization strategy and of how we upscaled the viscoelasticity. And to give you now a specific and clear example how this multiscale model works, for example, to predict the complex modulus and phase angle of asphaltic materials, of hot mix asphalt, for example. I show you here this slide. So we have as input parameter the mechanical behavior, the volume fraction, the morphology, and the interaction. We have to do some identification experiments on the binder scale. So here I already mentioned that we are using the DSR or the creep recovery tests as experimental results to fit the power law model. Then we can transform it. The viscoelastic behavior of the binder is transformed as explained in the Laplace-Carlson space. Then we can apply the homogenization strategy on the respective level. We have to back transform then the solution as mentioned in the last slide. And of course, we have to interpret it and do the interpretation. And of course, we have to verify our predictions of the multiscale model by validation experiments. But of course, these validation experiments, they don't have to be that huge as you have usually to do all these experiments on the asphalt on the macro scale. But anyway, because we wanted to be sure that we are doing the right things with our multiscale model, you see here we did a lot of validation experiments. This is a stock of all the different asphalt and binders we used for the validation of our model. And you see here we did different tests. Not the one thing is we did 4-point bending teen tests, and we have now already about almost 400 data points with different types of binders and asphaltic materials, modified binder, non-modified binder, and very different types of asphalts, drainage asphalt, and so on. And you see here a nice correlation between the experimental results of the predicted stiffness and the predicted stiffness from the multiscale model with the input parameter, just this simple viscoelastic model, the power law model from which is fitted from the DSR tests. Yes, and interesting is that we did also correlations with 4-point bending tests, not only with 4-point bending tests, but also with indirect tensile tests. And you see here the correspondence between the experimental results and the multiscale model is even better. Okay, before I make a short break and we'll ask for answers. So because it's now already, I'm talking now half an hour, and I know it's also for the students and even for the lecturer a little bit exhausting. I want just to give you or just explain to you the latest things we implemented in respect of combination where we try to combine now this multiscale model also with neural networks, because we have a lot of experimental data in our database from former tests with DSR, with stiffness tests on asphaltic on the different scales on mastics. And we feed that into a neural network. And you know, artificial neural networks are empirical methods based on the simulation of associative memory of neurons in the biological brain. So actually, first we use that to explain a little bit better the data from maintenance projects. But the idea was now to combine these neural networks with the results of the multiscale model. And you see here how this combination works. It's kind of deep stacking, how we call that. So the problem with the neural network itself is that it can also learn errors. So if you feed here errors in the neural network, also the output of the neural network can be erroneous, can be or is combined with errors. So the advantage is if we now use prediction methods like the multiscale model, that we can very much improve this precasting and the forecasting of, for example, stiffness, but also of our other performance parameters of asphaltic materials. You see it here. This is a validation result of a combination. We did it for the first time, and it's actually on publication this year, hopefully, or next year, where we combined these different methods. So learning from the results from the lab and also from the multiscale model. And you see, we have here an excellent fit of the experimental data and of the forecast of the neural network. Okay, so before I start with the upscaling of another performance parameter, so the first part of my presentation was very much related to the basics and also how we can upscale, for example, stiffness very easily with the multiscale model, and the newest developments, how we combined this multiscale models with neural networks. And the second part will be how we try to upscale another very important performance parameter, fatigue behavior of asphalt materials. So a little bit to activate you and to give you space to ask questions, I would be happy now to give space for your questions.
Professor, I'm going to start with a question in this break that we're having. Could you elaborate on why the model is working better for the IDT samples and not as well? It is also good, but it's better for the IDT than the 4-point beam samples.
This is a very good question. Honestly, I don't have an answer. I think it is related to the repeatability of the different repeatability of this type of tests. So we know that from the 4-point bending beam tests, we have higher standard variations in the test results, and maybe this is related also that the goodness of fit is not that well for this type of tests if we compare the 4-point bending beam test with the IT test, with the indirect tensile test. But we are working on that, and it's obvious in the slide. It's right here. Are there any further questions? Who is brave enough to answer questions? I don't know if I can. Who is brave enough to ask questions? I'm not sure if I can answer all of them, but I will try. It was already a long day for me because I just came from a board meeting of the university, and so I'm happy now to go a little bit back also to research and to teaching.
So we have a
any
question.
Questions?
They're asking if you could please go back to the power law once more.
Okay.
And clarify it again. Yes.
So you want me to explain the power law again, or this is a very simple rheological model. So we have a spring for the elastic property, and we have a nonlinear dashpot which is related to the viscous property of the material. And in combination in a serial, it's called the so-called the power law model. And it's easy to fit, for example, with creep recovery tests or from creep recovery tests or from simple DSR tests, dynamic shear rheometer tests. And I think it's a very common equipment in all of the laboratories around the world. That's why we choose this. But I will then show you a much more sophisticated material model where we already now where we are working on the upscaling scheme with a more sophisticated rheological model. But I explained that because this is was the first model we applied for this homogenization scheme.
Okay, we have another one about the, if you want to take it at the end, that would be great too, or no?
Okay, so should I continue? It's up to you. If you are all of you are already activated again and ready for the second part of the presentation.
Okay, I'll keep track of the questions and give them to you.
Okay, I appreciate that because so I can concentrate on my presentation rather on tricky questions. But as I mentioned, I hope I can answer all of them or most of them finally at the end of the lecture. Okay, so going back, upscaling fatigue behavior. This is the second part of my presentation because beside binder aging, of course, fatigue of asphaltic materials, and as final consequence, the structural failure of flexible road pavements, as asphalt pavements, is actually, I would say, the most critical performance parameter. And if we have a common sense that we call fatigue of material, is generally we define it as the degrees of material stiffness due to repeated loading, and that's of course the same definition we are using in the pavement engineering community. And usually the loading level, when we are talking about fatigue, the loading level is significantly smaller than the strength of the material. But due to the repeated loading, this fatigue happens. So this slide shows very simplified the mechanism of fatigue at the medium and usually at the medium and low temperature level. The fatigue process of asphalt or hot mix asphalt is believed to be mainly driven by what we call microcracks. This is the starting of fatigue, and we see a decrease in the stiffness of the material, of the dynamic modulus. And with continuous loading, a microcrack network, as shown in as I showed in the picture on the top of the layer, such a kind of microcrack network is believed to form itself, and finally these macrocracks arise, and they are leading to the material failure. So that's a little bit a definition what is fatigue and what we think is the mechanism behind the physical mechanism behind fatigue of asphaltic material and of asphalt pavement, of flexible pavement. And beside, of course, we have to acknowledge very tricky phenomena like self-heating, self-healing, binder dixotrophy, etc., etc. So I will not go into deeper in that. So we have different approaches how we can address fatigue in pavements and how we can describe them. Two main approaches are applied in pavement engineering, what we call the phenomenological approach, which is written down here in this slide, and the other one is the mechanistic approach, and I will go to come to that later in the next slide. So most of us are using this type of question, this type of relationship, this type of equation. I wanted to say, not question, equation. This phenomenological model is simply caused, is simply and used because of only the mixture response and the initial stage of the fatigue testing needs to be measured, and then we can easily apply that. So it's very simple to use, but actually it does not account for how the damage evolves. Actually, this type of phenomenological approaches are only strictly said only valid for a given set of testing or loading conditions. So actually, we should come over these phenomenological approaches and move forward to mechanistic approaches. And actually, in many design methods, this already happened. Happened. So in general, fracture mechanics or damage mechanics with or without viscoelasticity is adopted in the mechanistic approach to describe fatigue. Damage grows in asphaltic concrete. This approach is inherently more complex, of course, than the approach shown before, this phenomenological approach. But may be applicable to a broader range of loading and environmental conditions, and that's the big advantage. So that's the reason actually we proposed this new fatigue model for asphaltic materials and published that now already some years ago. Of course, we are working to enhance and improve this material. Because we tried here to combine for the first time fracture mechanics and continuum micromechanics. How does that work? To model the fatigue behavior of asphalt, the multiscale model based on homogenization techniques of continuum micromechanics was extended as shown here in this slide to describe the decrease in stiffness which we see in the material due to the loading, to the cyclic loading, to describe this decrease in the stiffness and the increase also of the phase shift angle, which we also see due to the fatigue of the material as so-called crack density parameter D, we see it here, is introduced, and it defines the number and size of microcracks on the mortar level. So we introduce here the evolving of microcracks at the mortar scale to define the degrees of stiffness and the slight increase of the phase angle we see in asphaltic materials during the fatigue testing. Very briefly here, we some continuum micromechanics, how we did that, and it's published elsewhere, so I will not go into deep, but we added to this homogenization tensor, which I already addressed in one of the first slides when I talked about the basics of the micromechanics. Here we added additional terms for the consideration of these microcracks. So we have the crack density D and a localization tensor for randomized crack distribution, which we introduced, as I mentioned, on the mortar scale. And the evolution of the crack density D we introduced, serving as input parameter for the multiscale model at this mortar scale, is described by the increase of the crack radius A. You see it here. So the number of cracks is related to the increase of the crack radius A. Hereby, a crack growth criterion for viscoelastic materials, according to Shapery, it's written down here, the law of Shapery, which is itself based on Barry's law. Probably, if you have already heard some classes in fracture mechanics, you should have heard also about the mathematics. And N determines the speed of crack propagation, and it's related to the viscoelastic properties of the material. And you see here, very important, so this is C, and we have here the JV, and the J integral is by definition the energy or work of fracture per unit area of the crack surface A. It's defined here, where WR, it's here, is the dissipated pseudostrain energy, the dPSE per unit volume of the intact material. And for the determination of this generalized G integral, we need to define the dissipated pseudostrain energy, WR, written here again, wherefore strains are transformed into what we call equivalent pseudostrain, WR1 and WR2, allowing us to eliminate the viscoelastic contribution to the dissipated energy. And the dissipated pseudostrain energy is separated into on the one hand, the change of the phase angle, and on the second, WR2 due to the change of the complex modulus. Therefore, the area of the stress pseudo energy, you see it here, and in the hysteresis loop corresponds exclusively to the energy dissipation due to the damage. And for a controlled stress test with a given stress amplitude sigma 0, these two contributions to the dPSA, to the dissipated pseudostrain energy, can be calculated. So we have, based on this separation, we can determine the generalized J integral. And you see here the validation of this multiscale model to address the fatigue of material on the mortar scale. You see here the experiment. We have both done 4-point bending beam tests and also cyclic uniaxial tension tests. You see it here on the right side of the slide at different frequencies and at different temperatures. So from -10 up to 20 degrees. And you see here actually a good agreement between the experiment and this model. So it seems to work that if we introduce this kind of microcracks on the mortar level, that we really can describe what happens during the fatigue in the material during the cyclic loading. You see here then that the model drifts away from the experiment, and we relate this to the development of macrocracks at the end of the fatigue experiment. Okay, this was a lot of theory. Let's also talk a little bit about the practical application, which is always very important for these types of models. So actually our goal, or I would say a little bit vision, to use this multiscale model of asphaltic materials is that we can use it as actually a highly effective tool for both for the mixed design and also for the pavement design. So for example, if we have here the aging behavior and the rheological behavior by very simple tests, we have here the aggregate gradation with the volume fraction, which more or less is related to the mixed design. We can then predict the viscoelastic behavior, the fatigue behavior. I showed you both how we can predict now the stiffness already and the fatigue behavior. What we are working on is also the low temperature cracking and the permanent deformation. I will come to that. We introduced that in a finite element model and can then do an optimization on that. I know it's already time for me. I have just a few slides if that's fine for you, okay? And this is, for example, already how we can apply our model, mixed design, for example, here to predict independence on the load frequency, the master curve of the same asphaltic material on the one hand with 3.5% of binder, and with the same binder, 4.5% binder. I can show a lot of, this is a very simple example, but you can now combine this with different binders, with new binder types, or with different grading curves, and you see the behavior of the material. And actually, this is what we wanted to address with this multiscale model. Okay, coming to the conclusion. So we could successfully implement such multiscale models. Actually, we found very straightforward homogenization strategies, and they are published. And actually, they run on a notebook, so a very standard PC. And we can now consider the changes of the properties of the constituents of asphaltic materials on the respective scale. And I think that's important. We don't have to do all this testing on the macro scale, but we can do the very simple tests on the respective scale. What I wanted to show you also is that we cannot only upscale stiffness performance, but we are working also to upscale fatigue performance. And here with this more sophisticated rheological model, where we also implement here, you see a plastic behavior. So we are working now on the model also to implement permanent deformation in our model to predict also permanent deformation. So we can optimize our material by this very elegant tool of a multiscale model. These are the first results, very fresh, where we already implemented this more sophisticated rheological model, and you see here also the plastic behavior can be modeled. Here we model the creep recovery test, repeated load cycling tests with the dynamic shear rheometer, or also on the macro scale triaxial cyclic compression tests. And we found very good results, and between the model and the simulated response or the predicted response from our new enhanced multiscale model. And finally, I want to acknowledge all the persons and excellent researchers who contributed. Of course, this is never the result of the work of one person, but also always of a huge effort of a team. Thank you for your attention. And now I'm happy for your questions. I hope I was in time with my presentation, and I could hopefully also give a little bit of the enthusiasm to you about this new model approach.
I think you certainly did. We have several questions. So we're going to start with Haoping Wang. If you could please ask your question on the audio.
Hello, can you hear me?
Yes, we
Yes,
can.
I can hear you. Thank you.
Yeah, this is Haoping Wang from TU Delft. Thanks for your presentation. I have a question regarding the input parameters for the macromechanic models. You mentioned that for the input parameters, you used the complex, the creep compliance. But normally in the lab, we have the data such as the complex modulus and the phase angle in the frequency domain. Can we just directly use this as the input parameter?
Yes, yes, we can. We publish this. I can send you a paper. You can directly convert it, and it's no problem. Yeah.
So we unless we have the analytical solutions of these macromechanical models, one thing I don't understand is why do you need the creep to use the data of creep compliance as you described in the first several slides, use the power law.
Why we are using the creep compliance and not, for example, the complex shear modulus, for example? I think that's the question. Yeah.
Yeah.
I think it makes sense. It made sense for us because you can easily calculate the creep compliance from the DSR test, so from the shear modulus, and transform it then in a very easy way in this upscaling scheme where we upscale the viscoelastic properties. And here we had an existing, and somebody's painting on my slides. And here we had, existing solutions how to transform the time space for the creep compliance to the Laplace-Carlson space and to back transform it with this so-called Stehfest algorithm. I explained it a little bit to you. I think that was mainly the reason why we choose the creep compliance, because we had existing solutions for this transformation. But for me, it makes no difference if you use the shear modulus. If we have, usually we, I mean, you can you have you can directly convert the creep compliance to the shear modulus or to the dynamic modulus of the binder. So for me, I think that the reason is simply because we had these existing algorithms. Is my question answered?
Yeah. Yes. Thanks.
Okay.
We're gonna have one last question from Anjali. She actually requests that you elaborate a little bit more on the model for the fatigue cracks, because it's clear for her how the cracks or how the damage is accumulating, but not how the cracks are starting, the initiation of these cracks. Could you elaborate on that and how you address it in your model?
I mean, let's start with the second part of the question. How the input in the model is that actually I explained it to you that we use this parameter D, which is related to the crack density, and actually we introduce different crack types randomly in the mortar phase with different area and with increasing load repetition. Of course, these microcracks are also increasing, and from that also the crack density factor D. So this is how we address it in the model. The first part of the question I didn't completely understand. Could you explain me a little bit how we you ask how we can?
Yeah, that part was clear. Like for her, it's clear how the damage is being accumulated, but not how it initiates. So I think you
how the damage initiates. I mean, simply spoken, in the model, it initiates with the first microcracks we introduce in the multiscale model. Yeah, how they. I mean, we never. We tried to look on the micro scale on cracks in mortar. Yeah, but this is really a tricky thing, and we think we detected some of them if you do it by at very low temperatures. Yeah, so if you cool down the asphalt after testing or after certain testing stages, actually we wanted also to really detect, to look at this initiation of cracks, but the mechanism itself, I'm sorry that I cannot answer you. So we know how we introduce them in the model and how in the model these cracks increase, these microcracks, but we didn't see it specifically in the material under the microscope. So I cannot give you a straightforward answer on that. So this is actually a hypothesis we are using about these microcracks. But I don't know if any researcher already detected some of these microcracks when they are initiating. Okay,
we're gonna wrap up because we're out of time. I just have one announcement for everybody to be on the lookout for an email, because the times of the seminar are going to be changing for the last 2 lectures too. They're going to be on Thursdays. They're going to be at night so that we can adjust to Asian work hours. So thank you again, Professor Blab, for the presentation.
It was a pleasure for me. Thank you very much for listening and for your excellent questions.
And see everybody.